Hello, everyone. Thanks for joining today's session. Where we are going to take a look at the Big.js library. Um, I a while ago I had one comment on my PR like, oh, maybe we should get the Big.js back again to this package to avoid side effects. And then I didn't have like a way to know for sure if we should use or not. So I decided to investigate a little bit more about Big.js and figure out how it works, possible side effects. And the idea today is to share some of the knowledge from my researches, and then that people get familiar enough to understand how to use this, when to use, when to avoid. So this is the main goal here for this presentation. Let me move to the next slide. If I find it, I'll find here. There you go. So what are the OTTs? So this is a space that we have here at White Prompt where we are able to share knowledge. It can be for some of the scenarios that we found during our project, some interesting things that we found out, things that might be useful for other projects. So this is a space to share knowledge, and it's great to see you here. And then for people that's going to watch this later in YouTube, yeah, that's great to share. And yeah, if you are watching this in YouTube, please like and subscribe. So yeah, so you are notified about next upcoming publications that we are going to do. So yeah, let's start. So what's the main issue that Big.js expects to fix? So in computer science, we have a known issue with floating point math. When we try to sum 0.1 with 0.2, then we compare this to 0.3, then it says that they are not equal. 0.1 plus 0.2 is different than 0.3. So and then this is not only for JavaScript. Before we start to criticizing any languages, this website says that, okay, your language isn't broken. It's the floating point math. And it's related with the way that computers processes binary values. And then this happens, this can happen for any language. We have some here like in C, then if we do like 0.1 plus 0.2, then we have 0.3 and a lot of decimal places ending in 4 here. Same for C#, C++, Elixir, Java, where is that? Go, and Java. So any languages can face this rounding issue with floating numbers. And how to fix that? So we have some possible fixes that we can do. If we round the values to compare and on our method result, this could be enough for some cases. So for this one, if we have here adding +1 with 0.2, then we have 3 ending in 4 here after a lot of decimal places. I believe it's 16. And then if we do to fix it, and then we do like 1 decimal place, then we have 0.3 without those extra decimal places, because to fixes is going to round this, and then it's going to return the correct result. So in case we do to fix it in both sides of the equation, then is this different than that? Then this is not. So this is one of the possible fixes. And then let's say that we would want to use this result from 0.1 and 0.2, and then we want to sum with something else. So here I added this result plus 5. Then for this one, we can see that here we are printing the result, which is this one, 0.3, the expected result plus 5. Then here we have a wrong result because it added 5 in the end as it was a string, because it really is. It's not a number, the result here, after we do the to fix it. So to handle that, we need to parse the result back again to float, so we can add correctly 5 to that number. So in this real result plus 5, then we parse the result 0.3. So this is float again. And then we are able to add or multiply for any numbers, and then it will handle the number. And then we add to fix it back again. So then we have 5.3 without possible wrong decimal places here. This is a possible solution. And it works fine if we have until 16 decimal places. Here I added 16 ones and 16 twos, and compared with 16 threes. Are they different? They are not. It's fine. But then when we do, if your requirements needs more precision on this number, more than 16 decimal places, then we will need to find a different solution, because here we see that I tried to add 20 ones and 20 twos in decimal places and added to fix it 20 the same way we were doing before. And then it does well until 16 digits, and then the last 4 digits it is not able to handle correctly. So here, this is a scenario where Big.js can be a good fit. So here I added like 100 ones and 100 twos, and then tried like V1 plus V2, and then set the precision to 100, and then we get like 100 trees. So perfect value for the expected result. And then for this part, I believe we can explore this next slides in the code. So let me bring the code here, and then we can play around with some of the values. This one. So actually, let's see one more. How to set up Big.js. It's quite a simple to add. We just need to do a npm install Big.js, and then we import this one. And then when we create a variable, we can do that using Big and the value inside of it, or add new Big and then the value. Both options look good, and both will work. And after that, we'll be able to use all of the existing operators that it has. And this is the first operator, district. So on the previous example that we saw that this one, If we try to add this number with this number, this is slightly different from the previous slide. They were between quotes here. And then this one is not between quotes, but the code looks exactly the same, except but this part. If we try to run that example one, then we can see that we get like 16 digits, okay, and then after that, everything is wrong here. It didn't add trees beyond 16 digits. That's one of the things that the strict method makes sure. So if we try to run this with strict, I think the next slide, yeah. If we set big.strict true, then it's going to complain about this number because it's going to require us to send between quotes here. And then this is a way to avoid wrong results. And then all of the values beyond that will require this to be between quotes. The decimal places variable, it allows us to determine how many decimal places we want to see after a division or a square root when we are compared with exponential values when negative values. So here we can determine any of the any number of decimal places, and when we run the code, then we see exactly the amount of decimal places expected. Rounding mode. This one is also interesting. It allows to set how it's supposed to handle values if we need to round the number. For this case, we have 3 values here to compare. V1, V2, and V3, they are 2.4, 2.5, and 2.6. And then by changing the rounding mode, we can choose between round down, round up, which would be the, let me share this one. It will be easier to explain this one. Rounding mode. Can I make bigger? Yeah, there we go. So it has 4 possible values here. If we choose round down, it's going to round towards 0. It's like truncating the value. So in this case, if we use it on that example, rounding down, all of the values would be 2. It would skip the decimal places and use 2. If we use round up, it's the opposite. It would be what we see on CL functions in some of the languages. It's going to round up every time it has decimal places. So all of those would be 3s if we use round up. And it has also two different ways of rounding when the value is in the middle, and sometimes we want to round up and sometimes to round down. We have the round half up. So this is going to round to the nearest neighbor. So here we have this example. There's one. Not this one. No example for. So here, if we round half up, then we can see that this value, it got rounded to 3. the variable 2. And because this is closest to the next value for the from the as comparing to 0. So is half up is going to round up in this case, while if we have half even, even is going to round to the nearest even number. So in this case, we have 2.5. So the possible rounding would be either 2 or 3. And then this is going to, the half even is going to say that for this case, we are going to round to the even. So this rounded to 2 in this case. And this is interesting because if we had like 3.5 here for all the examples, and we try to do the same, then the half even is going to round to 4, because in this case, the possible values could be 3 or 4, and then 4 is the even number, and then in this case, it rounds up. So it matches the half up result in this case. But some cases it can round to the to a different value because of it's going to try to get closest to the even value. Okay, next one. Okay, for those of you that learned Bhaskara and didn't know when to use that, then the possible case to use that is to learn a new tool for programming. So here we have like Bhaskara, probably everybody is familiar, b square minus 4ac, and then next can be, it will be minus b and can be my plus or minus square root of the delta value divided by 2a. So here is a small example that we can compare how to use that to get more familiar with the functions that the Big.js library provides. So we saw that we start instantiating the number with a big constructor, and then for this case we started with b, and then we need to do that to the power of 2. So the function that allows us to do that is power, and then we add the number of exponential value. Then this minus we do with the minus function. We are not to use the minus from the JavaScript language here. We need to use the big functions. And then here we are going to use 4, big with 4. And then this will be, when we want to multiply something, we use times. And then we are multiplying by a and then c. And we are going to print delta so we can know if we are doing good here. So we got 36 b square, 14, 16 for AC, for 20, 36, yeah, 36. So we are doing good with delta. And then next part of the equation is to find the roots. So for x1, we need minus b. To do the minus, then we can use this neg function. This neg function will do the opposite of the current values. So if b, in this case, is minus 4, this is going to be plus 4. And if we do twice neg function, then it will return to minus 4. It will do neg and neg again. It allows to compose many of the methods in sequence. Then this first one, we are going to do the plus function of delta. And then the next one will be the minus. those are the only difference from x1 and x2. So we need to find the square root of delta. So for that, we can use delta variable, which is already a big variable. So we don't need to say big delta. It's already type of this is already big. And then we find the square root of that. And then all of that, can see on the yellow brackets, they are involving everything here. So everything divided by 2 times a. So 2 times 1 here. This comparison with a equals 0 to throw the 0 is to we are not allowed to divide something between per 0 divided by 0. So we throw it these exceptions because this is if this is 0, this is not a valid value for the formula. And then, yeah, then we print x1 and x2, and then we got the exact results that we expected. Okay, so far so good, very interesting, deals with floating points pretty well, complex, high precision numbers, but what are the costs? Is there something that we should be aware of that? So then I was curious to check how it compares when creating many numbers. So those two examples, they are creating 10 million values, both of those. And the only difference is that one is pushing only the math random without using big. And then this next one is using the same math random number, but creating the variable as big. And then after run this, I added this start and end to compare how long it took for both methods. And this function gave a pretty close memory usage estimate. And then we can compare the results, and you can see that this one that's not using Big.js to create values, it took 116 milliseconds to create 10 million records and used 289 megabytes of memory, while the version with Big.js took almost 80 seconds, and then it used 2 gigabits to around 2.5 gigabits of RAM. So yeah, high precision is not for free. This is something that we should be aware of. And then from that, we can say that Big.js, it has a good documentation. They explain very well how to use the methods. It has a good support for high precision numbers. If your project requires this, this is a thing to keep in mind. Very powerful tool. It should be avoided in some cases where we have recursive calculations happening, things that will have lots of access at the same time and should have a good response time. So those scenarios where it's traffic intensive, it shouldn't be used for this one. And in between those two scenarios, it's up to development team to decide if they would prefer to use Big.js or to deal manually with the float point issues that might happen. And yeah, and for both cases, it's always good to have a good test suite to capture if something goes wrong. So yeah, the people is able to figure out the possible issues and fix that. Here I added some of the references I use it. And yeah, we are open to questions, comments, and suggestions.
Really interesting, Daniel. Awesome.
Excelente.
Nice to have the performance comparison, because without that comparison, I will bought Big.js, but now I'm thinking.
Yeah, we need to be aware of everything that we add to the project. It usually has a cost that we need to balance. Like, oh, this is cost worth what's going to fix, or should I avoid this one and try something else? So yeah, this is one thing that we need to keep in mind. Yeah.
Awesome.
Thanks.
Very small question. Do you know if it works with TypeScript?
With TypeScript, I didn't test that with TypeScript yet.
I'm just trying to know if it has TypeScript.
Yeah, I didn't find direct response for that, if it works or not. I expect that it should work, but I'm not sure. I didn't try by myself.
All right.
I'll take a look and follow up on that.
Yeah, all right. Thank you.
No problem.
Awesome. Luis shared that he's on a finance project and they must use Big.js for that. That was like the use case I was thinking on. No, finance.
Mm-hmm, yeah. For finance, yeah.
Awesome. Thank you again, Daniel.
Okay. Thank you. And thanks everyone for being here, for taking the time to learn to hear about Big.js, and hopefully this was clarifying for everyone. And yeah, if you have comments, suggestions, feel free to reach out. And blog part, if you are watching this in YouTube, please like, subscribe, and leave a comment below if you have comments, suggestions.
Awesome.
Okay.
Sorry, Jose, you were going to say something?
And no, I remember as well, this kind of technologies is used in the military environments when someone wants to send a rocket to other one. It's important precisions and that kind of thing.
I hope you're not using JavaScript. I hope it's not.
Good luck today, Brazilians.
Oh, thanks. Okay.
Bye-bye.
Awesome, guys.
Thank you. Bye.
Thank you. Great.
See ya.
Thank you.
See ya.